In this video, we're going to implement a simple solver for the fourth order Kuramoto-Shivasinski equation in JAX that is based on exponential time differencing. For this, we will look at the theory of ETD methods and then implement a simple class that can be called autoregressively and produces next states based on previous ones. Then we can roll out the solver to produce these very interesting and rich chaotic dynamics that the KS equation is known for. Let's get started. Hi and welcome to this new video. Today we will look at the Kuramoto-Shivasinski equation that has become a very interesting testbed for deep learning methods applied to physics simulators. But also in general, it is a very interesting equation and goes beyond what you're typically taught in numerical analysis because we have a fourth order derivative term in the PDE, and this makes this equation very stiff. So it is very difficult to integrate this equation and produce trajectories for it. And for those particular equations with a stiff linear term, there is a class of methods that have become kind of the de facto standard of integrating these equations, especially when we work with periodic boundary conditions that we use here, because then we are able to approach these equations pseudospectrally. So in general, the methods that we look at are based on exponential time differencing. And those methods are applied to equations where we have the time derivative on u is given with a linear differential operator applied to u plus a nonlinear differential operator applied to u. And we assume that the stiffness in the equation mostly comes from the linear term. So here we have the second order derivative, we have negative diffusion here, and the fourth order derivative, some sort of hyperdiffusion. And then we have the nonlinear term, which is a convection term that you might have also seen in the Burgers equation, and that can also be seen in the Navier-Stokes equation. The advantage of working with periodic boundary conditions, as said, is that we can use the Fourier space to efficiently evaluate derivatives. In order to use it, we will discretize our domain that we will let run from 0 to capital L into n+1 points and discard the last points to enforce periodicity, so we will have n degrees of freedom. The upper domain level L, or in general the length of the domain, is a very crucial parameter for the Kuramoto-Shivasinski equation in that it experiences different kinds of dynamics based on the length of the domain. Here we will choose L to be in the regime where the KS equation develops chaos. So the ETD method is not just one method, but a class of methods. But here we will look at the simplest one. So you can think of when you have classical ODE integration, you have an Euler method, which is probably the easiest you can do. Then this is the Euler for ETD methods. And it works like this, in that we get our state at the next point in time. So let's say the discretized UH at t+1 is the discretized UH at t multiplied with EL delta t, and the L is coming from our linear differential operator or its discretized form, and then plus E to L delta t minus 1 over L times the nonlinear part. Let's look in detail how we can use this method to solve the KS equation. So for this, let's introduce some abbreviations. So we will use d hat as our derivative operator in Fourier space. This is given by the imaginary unit times the wave numbers. And then we will build the linear differential operator very easily as minus d squared minus d to the power of 4. And we will get a minus here because the general form for ETD methods assumes that the parts that do not contain time derivatives are on the right-hand side of the equation. And in the KS equation, you see those terms are on the left. So if we move the second and the fourth derivative to the right, we will get the minus sign here. So this is something we can easily pre-compute. Then we can also pre-compute a coefficient, let's call it C1, and this one is e to the L hat delta t. And then we can also pre-compute the second factor, so this fraction here, which is the first coefficient minus 1 over L, and there is one wave number for which L will be 0. We can just set the value of C2 at this particular value to be the limit, and the limit when L goes to 0 of that fraction is delta t. So we will set c to this value if L is not 0, and we will set it to delta t if L is 0. There are also other approaches of computing these coefficients. In particular, this kind of fraction is something that can be numerically unstable when we have high discretizations, also under other circumstances. So please be careful about that. Okay, now that we have pre-computed all the quantities, how does our algorithm look like? So now we are given the previous state in time space, so just as is. And the first thing we do is we evaluate the nonlinearity in time space. So we will take UHT, square it, and multiply it with -1/2. And also the minus here arises because we bring the convection to the right-hand side of the equation. And then we take our nonlinearity evaluated state, denoted by tilde, as well as the previous state without any tilde, and transform it into Fourier space by the means of the fast Fourier transformation. So we will get a UH hat and a U tilde H hat. And then, since we did some nonlinear evaluation, it is recommended to de-alias higher unresolved wave numbers. So we will have a mask that is 1 for the wave numbers that are resolved and 0 for the wave numbers that are not resolved, to de-alias them. And typically what one does here is to keep 2/3 the first wave numbers. And then once we have that de-aliased, we will get the full result of the nonlinear operator by then applying the derivative operator, because so far we only took -1/2 UH squared, but it would actually be the derivative of such. So we will just multiply it with our discretized derivative operator in Fourier space. Once we then have that computed, we can easily advance to the next time in Fourier space by taking C1 times the U hat from the period state plus the C2 with this quantity. And this is basically the general form that we also had up here. And now we have the next state in Fourier space, which we can then transform back. And we've also used a nice idea that since we are computing the Ks equation, which is real valued, so in time space, the Ks equation should not take complex values, we can use the real valued Fourier transformation to save some computation here. For general reference for these methods, there is a very nice paper by Cox and Matthews, which has kind of unified the idea of ETD methods that has also existed in sciences before. And there have also been a couple of interesting follow-up papers you can, for instance, find with connected papers that go deeper into those methods. So let's get started, going into the first code cell, removing this hello world statement, and start with our imports. So we will need the JAX, then we will import jax.numpy as JNP, and then we will also import matplotlib.pyplot as plt. Shift Enter to execute the cell, and then let's define some constants for our simulation. So first we want to set the domain size to 100. So as mentioned before, this capital L value is crucial in that it defines the kind of characteristics or dynamics we will see for the simulation of the Ks equation, and choosing a domain size of 100 puts us into the chaotic regime. Then let's set the number of degrees of freedom to 200, and the time step size of the integration shall be 0.1. And then we are already good to go to implement our Kuramoto-Shivasinski solver, and I want to implement it in such a way that we have a class that can be called autoregressively, so that has a constructor as well as a call method which takes the state and produces the next state. So let's implement a class and call it Kuramoto-Shivasinski. And then start with the constructor, so the initialization routine. And I want this one to take self, of course, and then the domain length L as well as N and DT. And then what should it do? So first we want to save all these variables as attributes. So self.L is L, self.N is N, and self.dt is dt. And then for our domain, since we have periodic boundary conditions, we have our number of degrees of freedom, including just one of the two boundaries. So for convention, we will choose the left one, and then we can compute the dx or the element size as L divided by N. Then let's try to compute these values here, and it's easiest to start with the wave numbers K. So let's get our wave numbers. And since later on we want to use the real valued Fourier transformation, we also only need the real valued wave numbers or the wave numbers associated with real values in time domain. And we can get those by saying jnp.fft.rfft frequencies in 10 over n, so the n that we got as an argument, and then RFFT frequency is already choosing how many wave numbers we have based on these degrees of freedom. And then we have to provide the spacing, and the spacing will be L divided by n times 2 times pi. And if you're interested on why we need the 2 times pi, I have a video linked up here in where we look into the spectral derivative and that we need these additional factors here. Then we can define our derivative operator. So let's do self.derivative operator to also save it as an attribute. And this is the imaginary unit, which is 1j, multiplied with wave numbers. And then based on the derivative operator, we can build the linear operator. So the linear operator is the capital L or the calligraphic L that we saw here, and that was minus d squared minus d to the power of 4, which is based on the second and the fourth order term. So we will get it as minus self.derivative operator squared minus self.derivative operator to the power of 4. Then we can compute the exponential term, and this is something that I called C1 here. So this is the C1 that we saw here, and this will be jnp.exponential of dt multiplied with the linear operator. And then we can also compute this coefficient here, the fraction that I want to call coefficient here, or just coef, and we use a switch statement. So we say jnp.var because we do not want to compute it the same way everywhere. So you want to check where is the linear operator being 0, because if that is the case, then we would divide by 0, and in that case we will choose the limiting factor. So if that was the case, we will set the value to dt, and otherwise we will set it to the fraction, which is given by the exponential term. So self.exponential term minus 1.0 divided by the linear operator. And then finally, we need one more thing before we can go on to our call function, and that is the aliasing mask. So let's do self.alias mask. Here we will build a Boolean array by saying where the wave numbers are smaller than 2/3 of the maximum of the wave numbers. Sorry, they're missing a multiplication here. Maximum of the wave numbers. And then we can go on to our call method. So define the call method on this class, which takes self as well as u, and u shall be the state in time space. And then let's follow our algorithm. First step was to evaluate the nonlinearity. So let's do u non-lin, which is minus 0.5 times u squared. Then second step is to transform both the nonlinearity as well as the original state into Fourier space. So we will get first u hat by taking jnp.fft.rfft on u, and then we will get u non-lin hat by taking jnp.fft.rfft on u non-linear. Next step is the third one, to dealize the higher unresolved wave numbers. So we will get u, and we will just override this array, u non-lin hat is self.alias mask element-wise multiplied with u non-lin hat. And then finally, in order to get the nonlinear derivative operator evaluated, we will just take our standard derivative operator and element-wise multiply it with the u tilde hat. So we will get u non-lin derivative hat by taking self.derivative operator and element-wise multiply it with u non-lin hat. And then it's just a final computation to get to our next state in Fourier space, which is u next hat by saying self.exponential term. So this is the C1 coefficient multiplied with u hat plus self.coefficient, which was the fraction, multiplied with u non-lin derivative head. And then this is the next solution in Fourier space. We can quickly transform it back into the time space by saying jnp.fft.irfft for the inverse real-valued Fourier transformation applied to u next head, and n, which is the number of degrees of freedom in the time space, is something that we have to inform, and this will be self.n. And then we can return u next. And so basically, once we instantiate this class, we can call it, so it kind of becomes a function, and we can call it on state, and it produces the next state. And if we call it again on its own output, we can roll it out into a trajectory. So let's shift enter to register this class. Then, before we instantiate it, let's start by creating our mesh and initial condition. So the mesh shall be jnp.linspace from 0 to domain size with n number of degrees of freedom, but we want to exclude the endpoint. And that's just a convenience here. We could also select end-of +1 and then discard the last one, but here we will do it more verbose with endpoint equals false. Then we choose an initial condition. And here for the Ks equation, the initial condition is not too crucial because in the long term, we will see that the Ks burns into its chaotic dynamics. So here we will choose a sine wave. So let's say u0 is jnp.sine applied to 16 times jnp.pi times mesh divided by domain size. Then finally, let's instantiate our stepper and call it the Ks stepper by taking the Kuramoto-Szywaczyński class and instantiate it with L being the domain size, N being the number of degrees of freedom, and dt being the time step size. Shift enter executes that, and then we can plot our step. So let's start by first plotting the initial condition. So plt.plot on mesh and u0 and attach the label initial, and then we also apply the Ks stepper once. So plt.lot on the mesh and Ks stepper, and then we can use it as a function applied to u0, and then let's give it the label being one step. And then now I want to present to you this concept of autoregressive rollout. So we will just apply it again on its own output. So we'll do mesh and then Ks stepper applied to Ks stepper on u0. And this one gets the label 2 steps. Then let's get ourselves a legend and hit enter, and now gives us this plot. So as you see, the initial condition is no longer clearly visible because the other two functions overlay it, but we see a sine wave with 8 periods basically. And our solution is progressing, it is moving somehow, but it's not moving very far. So we need to do a couple of steps to really see the dynamics. And this is what our next step is about, to roll it out. So we will produce a trajectory. So before we do that, it is probably reasonable to JIT compile our stepper. So let's just override it and say JAX.JIT applied to the Ks stepper. And then we can call it, we say autoregressively producing a rollout, and that gives us a trajectory. So we will start at a current solution and we will set this current solution to be u0, and then record a trajectory by being a list that starts at u current or at u0, the initial condition. And then let's say for I, and let me scroll down, in a range of 2000. So we will perform 2000 steps. So including the initial condition, we will then have 2001 states or snapshots or frames, however you want to call it. And say u current is Ks stepper applied to u current, and then we will just take our trajectory list and append u current to it. And ultimately, now we have a list of JAX arrays, so we can now stack them together to get a matrix, and this will be trajectory being jnp.stack on the trajectory. So now this runs, and that's also reasonably fast, 0.4 seconds for producing 2000 frames. That's very good, I believe. So then let's visualize it. First, we will create a figure, and I want to set the figure size a little bit larger, such that we can nicely see our trajectory. And this one shall be 20 by 5. And then we want to do an imshow to produce the spatiotemporal plot. And for this, we will plot the trajectory transpose, because by default, it would plot it vertically in that the time runs upwards, but we want to have it run from left to right, because then we can visualize the longer trajectory more easily. Then let's set the color mat to red-blue, the aspect ratio to auto to fill the entire plot. Then the origin we want to set to lower, because otherwise imshow would show us an image, but we want to have the y-axis, so the space axis, running from the bottom to the top. And then let's also inform it about the extent, such that we nicely know the limits of our domain. So 0 to trajectory shape dot 0 times delta t. So this is the extent of the x-axis, which represents time, that starts at 0 and then goes to 2001, which will be the shape here, times dt. And then in space direction, we will go from 0 to 100. Then let's also fix the minimum color value to -2 and the maximum color value to 2. And before we plot it, let's also add a color bar and add the x label, or set the x label to be time, and set the y label to be space. And Shift Enter hopefully now gives us the trajectory, and we see these very interesting dynamics of the KS equation, in that first we start at our sine function, and over time we then transition into this chaotic regime where we have those kind of wave fronts, and they move and they show these very, very interesting patterns. And if you then kept going, we would kind of see these behavior all over. Let me quickly summarize the video. So this was a very simple implementation of an ETD method solver for the Kuramoto-Sieraszynski equation, where we chose the domain length in a regime where the KS equation experiences some very interesting chaotic dynamics. And we solved it with this ETD method, and those required us to describe the discretized linear differential operator in Fourier space, and also a way to evaluate the nonlinear term. And we used a pseudospectral approach, and pseudospectral means that we work both in the time domain as well as in the Fourier domain. So even if we are only given a state in Fourier domain, we still have to transform it back in time domain to evaluate the nonlinearity. So we do the nonlinearity evaluation in time domain and all things related to taking derivatives in Fourier domain. And we implemented a convenient class that is given us an autoregressive time stepper, and this prepares all the coefficient and terms and then just gives us a call method which we can call on a state to advance it in time. And we use that to produce this very beautiful autoregressive rollout. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more awesome content, for instance some extensions on the KS equation. In the coming weeks we will implement a higher order solver and use some very interesting techniques from JAX to make the rollout even faster and to produce multiple rollouts at the same time, which is a very handy tool for performing deep learning tasks on trajectories created from the Kuramoto-Sieraszynski equation. You will find the code to this video linked in the video description, and feel free to play around with it. Here you will now see similar videos, and I hope to see you in one of the next videos.